morning, everyone. Uh, so my name is Yusuf Saad. I'm from this building, computer science. Uh, I've been doing some work since the early 90s with someone who was in chemical engineering by the name of Jim Chelykovsky, who is now at UT Texas, Austin. So what I'll be talking about is some work I've been doing on time-dependent DFT. We've started doing this work with Jim Chelykovsky early on. We spent a few years doing real space version and the plane wave version, and then I've done some work with Stefano Baroni, who visited here in 2005, I believe, summer 5 or 06. We continued doing this work with something that had to do with using the Lanczos algorithm for TDFT. So I'm going to start with just very briefly what the problem is. Density functional theory basically is based on ground states. By the way, I'm not a physicist, so I'm going to be emphasizing the computational aspect. And this is just to give you a background of this. And so there have been generalizations that have been made for excited states. And this was done by actually in the 80s. And there are a few approaches. Essentially, the problem is one of linear response. So you perturb a system and you try to see how it behaves, how the perturbation affects it, and you try to see where there are poles in the system and where there are things that have a very strong reaction to that perturbation. So essentially, you're perturbing the system, and you have a certain charge density initially, and you're getting something that is perturbed in that form. You see down rho 0 plus epsilon rho 1, and you're interested really in the linear term, rho 1. And you can then calculate physical quantities from that. So the first method that has been used is essentially to just integrate the time-dependent Kam-Sham equation. So you have essentially, oops, I'm going backwards here. Sorry about all that. Okay, so you have an equation like that, which involves this Laplacian and then these other potential terms. And for each wave function, psi j, you actually integrate the whole thing in time. And you have a few of them that are computed initially from ground states. So these are computed separately. Done some calculation, we do that with the usual parsec code, for example. You got those, it's a lot of vectors, you keep them around, and then you could integrate. And then the problem is you have quite a few of these ODEs to solve. So it's very time consuming. So we actually gave up on this after a while. It was not a very suitable approach. It has some nice features, very easy parallelism. It doesn't use much memory, but it was extremely time consuming. So we didn't pursue that. And then a student of Jim was very interested in using this approach, which is Casida approach. And the reason why he was interested in this, interestingly enough, is that he discovered the conjugate gradient algorithm, okay, which is a very known algorithm in our field. But he said, no, we could do this. Then you could solve these systems that are complicated and expensive in this Casida approach. So he used that, and he was actually able to get some results that were very nice at the time. This was 1999, around 99, 98, I believe, even slightly earlier. So they got some nice results with that. And here's the calculation that you have. Here, just to give you an idea, the computational kernel looks like this. You have to compute a very large matrix, which is dense, which the term, you have three indices for the rows and 3 indices for the columns. The sigma and tau indices are spin indices, so you could probably just ignore them because they they double complexity. But then ij correspond to one state which is occupied and one state that's empty. So you have a lot of these pairs, and it gives you actually the size of your matrix. The number of those ij pairs you consider gives you the size of the matrix. And so it's a large matrix. It's indexed by pairs of one occupied and one empty state. And of course, you can see that this is going to be expensive to compute. This matrix is going to be very expensive to compute. Now, what is this integration you have here? You have those two orbitals, psi I and psi j, and then on the other side you have k and l. Those are your two things, your two pairs that you're considering. And for each of those, you have to compute an integral like that. And then you have this 1 over r minus r prime. That is a Green's function. So you can think that maybe there's some Poisson solve. You could do this with Poisson solver. That's how this student, Igor, came in and said that you could do this with solving with the conjugate gradient. So let's look at those terms a little bit. So this is just specifying what those ij's are. So you have from one part of the spectrum, occupied states, and some of the other part of the spectrum, and you select pairs like this. Don't select all possible pairs. Some of them have no meaning, but that gives you one. Then gives you one column. And for each of those entries in the column, you have an integral to compute. And the number, of course, if you take this in real space, then that's a lot of points. So I'll just give you an idea. So you have there are two terms in here. This one of the terms in the integral. If you go back to the equation a little bit here, the second term here is actually reduces. You have two terms. The second term reduces to a single integral because of the approximation they use, LDA. It's a local term. So I'm not going to mention that. It's a very simple thing to do. The second term is the one that is most time consuming, and that's where you have this integral to compute. And that, if you can decouple that in two parts. And the first one has to do with solving. If you take, for example, just integration with respect to r prime, then that corresponds to, when you have this integral with 1 over r minus r prime, it corresponds to solving a Poisson equation like that. So that means you could do this as follows. For each ij, so that's a column of your, or a row of your matrix, whichever, you solve one Poisson equation, and you do a lot of integrations. Okay, you have to do integrations have to do with these pairs, the KL now, and you have to do this integral here for each entry of the. So this is going to be explained a little more detail in a second. So then the reason now we use CG here, the reason we gave up on this approach again is that we could not find good ways of solving a system. It was really, you hit a wall at some point. You cannot go farther in the optimization because the CG was not a very, for this sort of systems, was not very easy to speed up. We tried a lot of things, it didn't work out very well. By the way, you have to compute eigenvalues. After this matrix is computed, then you need to compute eigenvalues of this large matrix. And this could be in the tens of thousands. For this, we just use Scalapack, which was not in good shape in those days. And I'm hearing it's still not in good shape in these days. I believe there is some work to be done there to look at a good version of Scalapack that works well for large matrices. OK, so just an illustration here. This is one of the systems you computed at the time. We have, for example, this hydrogenized silicon. We have, in this case, 86 occupied states and 154 unoccupied. Multiply those two numbers, and you get the size. This is the size of the matrix. Okay, and that's the number of Poisson equations you have to solve. Each of them is in a region. I forgot the discretization that's used here, but it's probably a couple of hundreds of thousands of points in the real space. So you solve the Poisson equation that many times. And for each entry in the matrix, you have an integration to do. Okay? So I was actually interested in looking at this back. I will show you a in a little while what we did to optimize it. What happens was the initial code we got from from Igor, the very first one, was not too well optimized. It's just really looking at sharing the load, and load balancing gave us, and then some other things with the consequent gradient and so on, gave us really a big boost in speed up. So now we went to a different approach, because the idea here is we use CG. That doesn't work very well. Why not use fast solvers? Fast solvers are order n log n cost. They're not too hard to optimize. It led us naturally to using FFTs, and this means really using plane waves, going back to using plane waves. And this gave us much better results in terms of time. So again, the bottom line is this Poisson equation that you have to solve. And this you could do if you expand the phi j, the psi I, and psi j in plane wave basis, then the solution is trivial. That's the idea. Solution is very easy to do because the Laplacian acts very easily with just the scaling on those plane waves. So now this shows the picture of what I was talking about here earlier. Ij and Kl are the indices of this matrix. For each Ij, you solve one Poisson equation, and then you have these integrals for each entry there. And the idea now is to expand the plane wave in each wave function in the plane wave basis. And then, as I said, then solving the equation is trivial. And you just have, there's a lot of opportunities for optimization here. One thing you could do, for example, is there's a decay property that you can exploit. There's also a nice, very nice thing discovered by one of the postdocs here. Said that why don't we, when we look at the solutions, the product of psi I and psi j actually is almost zero everywhere. It's actually when we have peaks. So there is support of this function where you don't have to worry, we don't have to do anything. And that leads to some nice speed up there. So this is just showing, I'm sorry for the quality of the picture here, showing the difference in time, just that the real space and the Fourier space give exactly the same result. This curve, as you see here, is just the one based on LDA. In other words, the ground state. So it's just to show that if you use the wrong method, it doesn't work. So just comparing here, it's just really showing that the two methods give identical results. And here's the time. So for the real space code took like 15 hours. This took like an hour and a half. So it's about 10 times faster. The initial code itself was about actually close to 6 times faster than the very initial code we inherited from Igor. So it's it could be like 50 or 60 times faster than the original code on the same machines. But there's a lot of things that went into this, by the way. So this took, let's say, if you think about 5 or 6 years to get all of this. And there are many people who worked on this, and I should mention probably the names here, who did the hard work. Initial work was by Igor Vassiliev. I'm just showing the student and where their affiliation. He's a chemical engineer, student of GEM. And the real space code was worked on by, optimized by Russ Burdick, and then Shiv a little bit, not too long, on this. And then Shiv took over the FFT part. Started by Emmanuel, actually, who was a postdoc here, very bright postdoc. Who's now in Canada. And Shiv joined the company. I don't know where he is now because he moved companies. He was a student here, so they put a lot of time on this. And then Murillo gave us some nice hints on the physics side. Okay. Now, as I said, I collaborated with Stefano Baroni, who came here, I think, in 2005. And then what he did was, his approach is slightly different. And I have to say, the details are complicated to me. The framework is really complicated. I'll just show you, again, emphasizing the computational problem. He writes everything in terms of this thing called the Liouville approach, quantum Liouville equation approach. So you write, this is again the time-dependent Schrodinger equation that comes